Okay, great. Find the equation of the tangent line at 2, 6. F of x equals 3x squared minus 5x plus 4. All right. Equation of tangent lines. We did kind of review that a little bit earlier, but what do we do there? What do we know about tangent line? I need to do the derivative, which would be 6x minus 5. And what does that derivative give me? Slope of the tangent line. Yeah. So this will give me the slope of the tangent line. And in this particular case, I want it at 2, 6. So what do? My slope of my tangent line is going to be 6x minus 5, but at 2, 6, what is it? Well, yeah, the x is 2, isn't it? So I plug in the 2 for my x, and that gives me a 7. That's the slope of the tangent line. So if I want the y equals mx plus b, I can plug that in for m. One way to do it, then plug in x and y to be 2 and 6. Oops. And so that would be what? Negative 8 is b. So it's y equals 7x minus 8. Slope and tangent line there. Sound right? Okay, number 9. Find the critical numbers. Critical numbers. What do we know about the critical numbers? Numbers. Derivative equals 0, or where derivative does not exist. Yeah. So yeah, I need to find the derivative once again of this particular function. How do I do that for square root of 9 minus x squared? Chain rule again. Yeah, this, think of this as 9 minus x squared to the 1/2. So a little chain rule. Bring down the outsides 1/2 power, so bring down the power and subtract 1 from the power, so it'll be negative 1/2. And then the inside stays the same. It's still 9 minus x squared. Then I have to, though, multiply by the inside derivative. So the derivative of the inside, negative 2x. Which, that's nice. Those will cancel. The 2's will. And probably, let's think f prime as, this would be minus x over, wouldn't it, the square root of 9 minus x squared? Think of it in those terms. The minus power is right. And just flips it over. Makes it a square root on the bottom. Right? Yeah, so I'm trying to find the critical number. So the critical numbers, I set the derivative equal to 0 and solve. What about that? Well, that's an easy one. If you cross multiply, you get minus x equals 0, so that's just x equals 0. So that's an easy one. But does not exist. Yeah. And the ones we really looked at was where the denominator equals 0. Where the denominator equals 0, in this case, there's a lot of times one to look at. So where does this denominator equal 0? Well, it'd be where the square root of 9 minus x squared equals 0, which square both sides is just 9x squared equals 0, which where would that be? Plus or minus 3. 3 or negative 3. So you got 0 is a critical number, 3 is a critical number, negative 3. Does that make sense? Okay, well, that are some of our nice little word problems. Number 10, the volume of a sphere is increasing at a rate of 8 centimeters cubed per second. What rate is the radius changing when the radius is 80? Note the volume. Okay. I'll give you the formula, which is actually one we just got through finding out why that's that way. But yeah. What is it we're looking for here? We're looking for the rate the radius is changing. Well, in terms of calculus, how would that be written? The rate at which the radius is changing with respect to time, dr dt. Yeah, dr dt is what I'm looking for. I'm looking for the rate at which the radius is changing with respect to time. So I'm looking for dr dt. It says the volume is increasing at a rate of 8. So what does that tell me? That's dv dt, isn't it? The rate at which the volume is changing is 8. So that's dv dt. And then, of course, I want specifically the radius of 30, 80. So that's all the information provided. So how do I find this dr dt? So I ddt both sides, right? I get dv dt. Yeah, if I want dr dt, I better ddt both sides, all right? So if I ddt v side, the v side, what does that give us? dv dt. Yeah. The derivative is just 1 about with respect to t. What about this side? 4/3 pi is a constant, so it's just along for the ride, isn't it? So I need to ddt that, basically. R squared, what would that be? 3r squared dr dt. Threes cancel. We got dv dt is 8. We got 4 pi. We know the radius we want is 80. So we do 80 squared dr dt. Plug those in, right? So it looks like 8 equals, that'd be 6,400. 4 times that, was it 25,600? Multiply those two. Is that right? Okay. So it looks like 8 divided by 25,600 pi is dr dt. Not much of a increase going on there, is it? Slowly but surely. Oh, and the units, huh? Oh, yeah, we could reduce by 8, couldn't we? $3,200? 1 over 3,200 pi. All right. And units-wise, what are the units of that? The units of R divided by units of time. Okay? How's that look? All right, 2 more and we're all done here. Farmer with 500 feet of fencing wants to enclose rectangular area divided into 3 pins as shown. What are the dimensions that would make the largest? All right, so we know that the fencing we've got is 500. What do? We want to make the largest total area that we can. Well, one way to look at it is here I've got 2 dimensions. I've got the x and I've got the y, or vice versa. X is along the bottom, I called it, and y is along the top. We want to make the area largest we can. The area here, if I do that, is just xy, isn't it? So I want to maximize the area. How do I find the maximum? Where does the maximum usually occur? At the critical numbers. Yeah, I want the max area, and the maximum or the minimum usually occurs at the critical numbers. That's one thing the critical numbers are good for. One thing, I didn't mention it, but it's in the sheet there. The critical numbers also tell me local maxes, local mins, right? Using the first derivative. What does the second derivative tell me? Inflection points, we find the inflection points, but also concavity, concave up. The second derivative is positive, concave down if it's negative. So that's another thing for the critical numbers, or what you can use a derivative for. I don't have one on here, but don't forget those. There will probably be a local max, local min. Increasing and decreasing also is told by the first derivative, right? Positive means increasing, negative means decreasing. All right, but anyway, this is another use for critical numbers. Yeah, the critical numbers are, of course, at the derivative, set to 0 or does not exist. Could also be. But the problem here is, to find the critical numbers is what? I've got an x and a y. I need to get it in one variable. How do I do that? Well, I've got this fencing here. I know there's a fencing equation. The fencing equation, if I've got this, the fencing, what have I got? 2x and 4y's. And I know that the fencing is 500. So yeah, there's another equation I can use. And the way I'd use that is to get rid of one or the other, x or the y, or solve for x or y. If we solve for y here, what do you get? 500 minus 2x over 4 is y. Which I could, let's see, I went the other way. Get the x equals. Either way, I wouldn't have no fractions. Either way. Yeah. Yeah. All right, so A equals x times 125 over 2 minus x over 2. If I were now replace my y by this y equals equation. Question? No, it's just 125. Yeah. Just x over 2. There's only one fraction. Okay, thank you. Yeah, reduce the by. Okay? Just checking. All right, so yeah, now this is a nicer one to get the derivative of. Distribute your x, so it'll be 125x minus x squared over 2. So the derivative then would just be 125 minus, it'll be a half times 2x, which will just be x. Right? So now what do I do? Well, I'm trying to find the critical number. So instead of a 0. And that works out nicely. Just be 125, doesn't it? What was the question? What are the dimensions? All right, so the x dimension is 125. The y then is 125 minus x over 2, so that would be 125 minus 125 over 2, which is 125 over 2. 62.5 feet. So the x is twice as long as the y dimension. Huh? Yeah, technically should check to make sure that's a maximum. But since you bring it up, how would we do that? How could we make sure this is a maximum? Yeah, right. Yeah, what it means is, yeah, there's your critical number at 125. If that's then what do I have? I have, over here, I have increasing followed by a decreasing. So the derivative here is positive, derivative here would be negative. I can't check on either side there. Technically speaking, yeah, when you're finding a maximum, that's what you should have. A derivative and a negative derivative on the other side. And we could check that, like here we could go, well, we could just use 0, couldn't we? Here's my derivative. So at 0, I'd be at 125, wouldn't I? The derivative equals 125. On this side, something like 126, be 125 minus 126. Hey, yeah, that's going to be a negative, isn't it? So you've got a decreasing part. This part over here is increasing. So, yeah, that's next. When we got to these, I don't think we really okay? In our lease, our good old ship problem here. Ship A is sailing south. How fast is the distance between them changing at 11 a.m.? That's at 8 a.m. Time is on 3 hours. All right, so yeah, what we did is you let that distance the ship travels, let A be the x, and then let A be x, and then the distance the B ship travels y. Looks like a nice right triangle, doesn't it? So this is distance C. And what is it we're looking for? How fast is the distance between them? That's z. How fast is that distance changing? So I'm looking for dz dt. That's what I'm looking for. All right, so how do I set well, let's go back before. I've got x, a squared plus b squared equals c squared. X squared, so this is my equation. Now, I do know the times, and I could figure out x and y here, but I don't want to do that. Don't substitute until you do what? Take the derivative. ddt both sides. Because I'm looking for dz dt. And so if I don't have z in there, I'm not going to have dz dt, you see. I can figure out what x and y and z are, but if I plug in those numbers, I'm not going to get a dZdt, and that's what I'm looking for. So don't do that. So I'm going to ddt both sides. So that would be 2x dx dt, all right? Plus, what's this one be? 2 times y plus 50 to the third times 1. The inside is equal to 1. And then dy dt. With me on that? Y to the fifth, y plus 50 dy dt. And then the derivative of z squared. Huh? I think it's easy. You could, but that's going to mean you have to FOIL, and then you have to do the derivative, so it's kind of, this is saves you a step. Okay. Yeah, so, and the other thing it does, if you leave it like that, is these 2's cancel out, so you get rid of all the 2's. Now what do I do? Now we substitute. Yeah, x, what's x? X is the distance A travels. A is going, what does it say A is going? 20 miles per hour, 4 hours, and x is 60. Speed travel from 5 miles per hour, 5. What about z? Z, I have to go back to the Pythagorean theorem again, don't I? I have to use this again to find the z. So I've got 60 squared plus 75 plus 125 squared. 1565. Substitute those for x, y, and z's. What about the dx dt? Do I know it? The rate at which x is changing. Dx dt is what? It's 20, yeah. The rate, it's sailing south at 20 miles per hour. 20 miles per hour, that's the rate of x. Dx dt is another way of saying that, isn't it? So x, dx dt is so whatever. Dx dt is the rate at which x is changing. Y plus 50, so it'll be 75 plus 50 again. Dy dt is the rate at which that's the rate of 1525. V is the square root of 19,225. And ddt is 20. There you go. 1,200. 125 times 25, 3125 equals the square root of 19,225 ddt. So it looks like I got, what, 4325 divided by the square root of 19,225 ddt. Miles per hour. Did I do that right? Been having a few of those today. Everything look okay?